All right, today we're going to be doing random variables, and random variables is a pretty expansive topic. I don't know that I'm going to do it as much justice today with you as I possibly could. It shows up on the AP exam so often, and every time I find one of their problems, I always feel like it's somewhat different from anything else that they've given before or that I've put in front of you. And I feel this urge to show you all of them, which is clearly not possible. So best I can do here is to run through, what we had learned in a very, very, cursory way. So if you need to fill in any gaps, you certainly can go back and review. I'm here to answer your questions. But this is very, very important, and it may even highlight why maybe working through those practice AP exams that I posted might be a really, really good thing. So we'll start out with discrete random variables, and discrete random variable x has a countable number of possible values. So 4 kids, 8 kids, 10 kids, 2 kids, whatever. Okay, they're integer values, and we can count them. Probability distribution looks like this. Remember, it's just a table where the values for your random variable occur here. So if we're looking at number of boys in 4 births, that would be 0, 1, 2, 3, up to 4. And there'll be some associated probabilities that go with it. So all of these should add up to 1. Well, we'll get to that. So the requirements, the probabilities of P sub I must satisfy 2 requirements. And all of these will be your little P sub i's, like probabilities for the individual outcomes. All right, they have to each be a number between 0 and 1, so they meet the rules for probability. And if your table is complete and it shows a complete sample space, the sum of all of your probabilities should be 1. All right, if then, and this is what distinguishes this a lot from just basic probability, we would then ask a question like, what is the probability of having at most 2 boys out of 4 births? Well, we would have to add up the P sub I for 0, the P sub I for 1, and the P sub I for 2 in order to fulfill that question. So this is what this is saying. You find the probabilities of any event by adding the probabilities, or the little, probabilities per individual outcome of the particular values of x that make up that event. So here's an example. Number of patients seen in the ER in any given hour is a random variable represented by x, so anywhere from 10 to 14, and there's nothing left out here, is what could show up in the ER, and here are the probabilities associated with it. So we'll just check 0.4, 0.6, 0.8, 0.9, 1, 0.0. That is a complete probability distribution. So we can start asking questions. What is the probability that in a given hour exactly 14 patients will arrive? Well, the P sub I would just be this one value, so 0.1. At least 12 patients arrive, that means 12 or more. So 12 or 13 or 14, or means plus, 0.2, 0.3, 0.4, there's your answer. And at most 11 patients arrive, that's 10 or 11, right? So add up 0.4 and 0.2 and you get 0.6. So pretty basic stuff for discrete. All right, mean and variance. All right, if you're given this probability distribution, to get the mean or the expected value, you just take your values for your outcomes for your random variable and you multiply by its associated probability, and you keep doing that and you add them up and you get your expected count. All right, to get your variance, you just go ahead and take this value for the mean, subtract it from each value of x, value for x, square it, and multiply it by its particular probability. So you take this particular value for your random variable, subtract the mean that we got, take that difference and square it, and then multiply it times this probability. And you just keep doing that until you just complete the whole thing, add them all up, and you get your variance. Of course, most problems don't care about variance. They want the standard deviation. So once you get this single number, take the square root and you get some kind of idea of spread in your random variable. Okay? But we want to calculate these things on the calculator because these formulas are a little bit kind of unwieldy. So here's the previous example. How would we get the mean and the standard deviation for this particular random variable? All right, what I ended up doing was, put them in the calculator, and I labeled this values for x, so 10 through 14, and p is just going to be the associated probabilities. So if you want to play along, go ahead and pause, get your calculator out, and input that. All right, from here, we're going to go ahead and go to the home screen, and we're going to link this up to a calculator page, and we're going to do a one variable stat. And it's going to be a little tricky, not too bad. So go to Menu, Statistics, Stat Calculations. Of course, it jumps the gun on me. So Menu, Statistics, Stat Calculations, and one variable statistics. All right, the number of lists will actually just be 1, all right, because we're trying to find the mean of the values for x, and they're just in one particular column. So we'll hit OK. So the x list here was just going to be x. And the frequency list, we're going to put that in as p. So we'll right arrow here. We can delete that and just choose P. I have some other things stored in here, so you probably don't. No category lists. We don't include anything for that. Okay. So looking at this, this is going to be the mean that we would expect in any given day. And you notice that your standard deviation is undefined. That's because we're not dealing with sampling and there's no sampling variation. So we are dealing with something that has an exact number, which would be a sigma. So this is your standard deviation. If you want variance, just take that number, just square it. You don't need anything beyond that. It doesn't need to be utterly perfect, but just take this number and square it to get variance. Okay? All right. So back to what we were doing. All right, more about means and spreads. If you add or subtract a constant from data, it's going to shift the mean, right? It's just going to take your distribution and move it up and down on some horizontal axis. Think about it this way. It's a horizontal shift. All right, so in order to get the mean from adding a constant to all the values for your random variable, you just take the mean that you had originally and add or subtract the constant to it. Okay, so it could be plus or minus. All right. However, if you add a constant to every single value for x and check out what the spread is going to do, well, all it does is this moves it left or right on a horizontal axis, but it does not dilate it. All right. So yeah, it's just going to be your original variance for x. So adding or subtracting a constant is superfluous. It does not change your original value for variance. It will change your mean because mean is a measure of where something is centered, more or less, and variance is spread, and you're just moving the spread up or down without actually changing the spread itself. However, when you multiply each value of a random variable by a positive constant, it's going to multiply the mean by that constant. So if you take all of the values that you have for your random variable and multiply by a constant, the mean is going to be affected by taking the original mean and multiplying it by that constant. All right. For variance, however, that value of a comes out, and since variance is squared units and that multiplier isn't, you have to square that and then multiply it to your original variance to get the new variance. So these are formulas that you need. You just basically need to memorize these. All right? So this is what happens when you change things by adding or subtracting a constant or multiplying by a positive constant. All right? So you need that. All right, so when you combine random variables, this is different. All right? the mean of the sum of two random variables is the sum of the means, all right? So you would just, if you want the mean of adding or subtracting x plus y, it's just going to be the mean of x, the mean of y, and you either add or subtract them depending on what this is. So again, the mean of the difference of two random variables is the difference of the means. It's summarized right here. Now you got to be careful with variance, all right? If the random variables are independent, the variance of their sum or difference is always the sum of the variances, okay? So the variance of x plus or minus y is just going to be the variance of x plus the variance of y. Spread is spread, whether it's negative spread or positive spread. So it doesn't really matter. You're not going to decrease spread by adding more onto it, whether it be positive or negative. So both plus or minus will end up being plus for the original individual variances. So this is important to remember. It shows up all the time. This just makes intuitive sense. This might not. You just got to memorize it. All right, that brings us to continuous random variables. And continuous random variables take all the values in an interval of numbers. So whereas your discrete random variables were only countable values, so you had 1, x is 1, then x is 2, and all the probability for 1 was just piled up there, and all the probability for 2 was piled up there. There was nothing in between. But for a continuous random variable, you have a meaningful 1.2 or a 1.3 or a 1.8, okay? So it's different. Since there are so many values in between, integer values, you can't possibly put them in a table of values. You have to describe a continuous random variable, that probability distribution in a density curve. Density curves that we covered were uniform or normal. All right, so for example, let x be a random variable between 0 and 1 produced by a random number generator. Not sure what this extra period's all about. And so here we go. All right, so remember area, this would form a rectangle where we have length times width. And since this is 1, this will have to be 1 also. But this horizontal axis doesn't always have to be 1. It could be 10, in which case your vertical axis would be 1/10, because 1 times 1/10 would give you an area of 1. So these both have to have an area of 1. So if we want what is the probability with a random number generator of getting a number between 0.3 and 0.7, it'll just be the difference between these, which is 0.4 times 1. So the probability or the area is 0.4. Here it's either x is less than or equal to 0.5, which would be 0.5 here times 1, or 0.5. And then 1 minus 0.8, x is greater than 0.8. That would give you 0.2. And so the total here, since it's or, would be 0.7. All right? Now keep in mind, I'm about to show you that x being greater than 0.8 and x being greater than or equal to 0.8 will give you the same area here, all right? So when x is a continuous random variable, there is no difference between less than and less than or equal to, because the difference here is going to be this line here. And a line geometrically has no area. It's got length, but it has no width. So it's a kind of a meaningful thing. All continuous probability distributions assign a probability of 0 to individual outcomes. So if I ask you what is the probability that x equals 0.5, the answer is 0. So whether it's there or not will not affect, whether it's less than 0.5 or less than or equal to 0.5. You get the same area and the same probability. Just a little fact to know and tell. All right, normal distributions are density curves. They can describe a random variable. So we can, and we did this when I was doing standard normal calculations yesterday. I was defining a random variable as x, being approximately normal with two parameters, mu and sigma. And when you standardize it, it just goes into standard normal values. So that would create z being approximately normal with centered mu at 0 and standard deviation of 1. That's how a z curve works. It's centered at 0 with a standard deviation of 1. All right, when it comes to these things, I'm not going to go into a whole lot of explanation with these because they pretty much work the same way they did yesterday when I closed out the PowerPoint for yesterday. I did a bunch of standard normal calculations, and it's exactly what you would do if you decide to call those standard normal calculations, random variable x, right? So, but continuous random variables follow the same rules when combining random variables. We may see this on Thursday, all right? So, examples. I'm going to hit pause here, and I'm going to set up for these examples.